who? Sam. Sam.
Oh no, actually, I think we can record.
Yes.
Sam, could you please give a right to record to Pavel?
Yes.
Actually, I think.
Yes. Already. Yes.
I think I already have this right somehow.
By the way, now
Maybe
we
we will
are in condition of revolution here in Russia, as you know. So how it is related to the course, YouTube seems to be blocked today in Russia.
Oh.
So still we have a Chinese backup, right, Sam? So in the
Yes.
case of the blocked YouTube, you could use Chinese backup. So we are actually prepared for the revolution. Okay.
So what is the okay?
But
So
But I-
revolution. You see, so real professor actually ignored revolution. He should be interested only in the subject he is trying to explain. Okay.
but I think recording makes Zoom, so Zoom will put it on the YouTube anyway. It's in cloud, so it's okay also from the European point of view.
Ah, yes. So right. So only Russians suffer. Okay.
And it's possible to make backup on other sites with videos in Russia.
Okay.
In general,
Okay.
it will work.
Okay. So I'm trying to act as a real professor. So real professor is interested in revolutions and all this stuff only in relation how it interferes study, right? Okay. So so based so let us start recording.
They're already recording.
Yes.
Okay, so based on the exchange yesterday, I decided that probably I go too fast. We actually have time, yes? So we should devote more time to details and examples. Okay? So the plan of my today's talk would be more of so-called Landau-Ginzburg stuff. Story. So since I took your attention explaining something about Landau-Ginzburg, so-called Landau-Ginzburg, actually theory with the superpotential, you see, I need to give you more. So you, such that you properly invested your time yesterday, okay? So you should increase your understanding. And that's why I'd like to do the following things. 1A, examples of singularity theory. And explicit examples. Point 1B, gravitational descendants.
I think we're out
Point
of focus a little
1C.
bit. We're a bit
What?
out of focus. A bit out of focus.
Okay. So
Okay.
camera is out of focus. It's
No.
not me who is out of focus. It's the camera who is out of focus.
Now it is better right now.
Okay, gravitational descendants. And here we will see how gravitational descendants related to this KP hierarchy. Okay, we will get all this here. Point 1C. Point 1C would be Kyoji Saito, higher residue pairing. So actually, when people say higher residue pairing, they think that it is because of the higher residue. Actually, there are two H's in one H. It's not just higher residue pairing because it's multidimensional residue. It's also higher residue pairing because it is a sequence of pairings. Okay? And from this, I think somebody came in, and from this, you would see how to compute it. So it happens that I computed it first many years ago, and QGIS just guessed it, and from this higher residue pairing, you will see so-called cyclicity of infinity operations, and also flatness of the metric. Why I want to explain this? It's not because you may be interested in the flatness of the metric, but there are actually several reasons to explain this. First, 1C1, you can check that cohomology of d bar plus dw do not change as a vector space. Second, of course, flatness. And let me remind you that this flatness or cyclicity is important in order to go from solution to what we call oriented associativity. Well, this is associative. To potential associativity that is called associativity. It is needed to get this thing. Moreover, this flatness and this cyclicity is needed if you want to go to higher genus. The reason 3, it is that the way to get it, I mean that higher residue pairing, allows you to go to ambit-Twistor strings. You know, lemma, it's interesting that lemma sometimes could be applied in some other place. So that's why I have a good reason to explain not only the statement, but the lemma. So how to compute it? So this line was absolutely unexpected for me. So I am going to tell you all this, okay?
Sorry, is it possible once again to reposition the camera? We once again can see the right part of the board.
Right is here.
Yes, yeah, from us, right.
Okay.
No, once again left, it's the same. It's like it was. No, other direction, a little bit more. Now it's okay. No, it's okay. Thank you.
So this
I don't know, for some reason, for me, it's more convenient to write here than to write there. You see, because I have this margin, but I'm always not getting here. Or we have Jianping. Okay, good. Nice to see you.
So this non-changing of cohomology is very counterintuitive if you sort of compare to adding a flat connection to a drum differential.
Yes, yes. And all this is kind of localization. Okay? So I'm sorry, you see, all this was a piece of Landau-Ginzburg story, but being realist, now I see that if I would not run too fast, it's exactly what I will be able to explain. So if I'll have time, I'll explain more. But at the moment, I'll explain this, okay?
Mhm.
So let me recall the setting, okay? So the setting was, we studied the following pair, d bar plus dw1, and d plus d bar w2 bar. And we studied the pencil. And we call this QZ. So let me recall that pencil typically appears when we study the following pencil. Suppose we have a drum operator, and we have operator of contraction with a vector field V. Where V is a vector field that represents U1 action. So this thing is called Cartan equivariant differential. So this is this thing that I call dz. dz square is what? Is of course z times lv. So it is a differential when it is acting on what? On U1 invariant differential force. Let me write you the geometrical picture. So geometrical picture is as follows. You actually have a U1 bundle. Here you have Y, and here you have base that I call B. Okay? So, so what would you have on the base? On the base, you have cohomology. So we study cohomology of the base. That I called HB. Okay. And then there is specific class in the cohomology of the base. Special class. That is called first Chern class of the bundle Y. Okay? And there is a well-known statement that if you study DZ cohomology, then, so DZ cohomology is a moduli over C of Z. Okay, and the action of Z is the action of the multiplication of the first Chern class. Okay, so I think you know this. I just recalled. Now, so how this is related with what I wrote here? This is related in the following way. This was Q in topological string. This was for the case when W bar equal to 0, G naught minus. So this cohomology corresponded to for W bar equal to 0. This cohomology corresponded to what? To okay. HQZ. It's a space of local observables. In the topological string. When such that if a class O that belonged to HQ of Z was Z of O tilde, then O corresponded to what? To so-called psi class or tau class. I prefer psi. Some people prefer tau. Witten used sigma. Since I'm a physicist, I'll use sigma. It's called Marita-Mumford. this class corresponds to the following. So here is the Riemann surface. Here is the marked point. Here we put operator O and some other operators, OI. And then we have the integral over this moduli space. And this equals to integral over the same modular space where you have psi 1 at L1 times O tilde and the rest. So it means, so this is called gravitational descent. Or Mariti-Marfos class. So the story of this gravitational descendant was as following. In the year 1988, I think, or 89, Edward Witten was thinking about so-called topological gravity, where you had to integrate over the moduli space. And simultaneously, people were doing matrix models, where they found some matrix computations for some string theory. Edward Witten had a great intuition. At that moment, he did not believe in matrix models. At that moment, he thought that everything should come from differential geometric constructions. And he believed, it was actually a belief, that he would be able to reproduce results from the matrix models using some kind of topological theory that he was developed at that moment. But the problem was that if there is no matter, and if you have a moduli space, he thought that it's impossible to find any observables. And actually, he wrote a paper with Labastida and maybe with somebody else, I don't remember with whom, who was the third author, saying that, sorry guys, no observables, nothing to study. And then there was a man called Perival. I think like this, or with V here. Okay, please excuse me for not remembering the exact letter. So he would not be mad on me because I forgot the letter, but he would rather be grateful for me that I remember his work. Because he wrote a paper, look, there are observables that you can use in topological theory, and these observables are exactly these classes. It means just suppose that you have only these sigma ones or first Chern classes of the line bundle. They are observables, local observables. You should use them. And then Witten came up with another paper that was written in a rush, when he was not explaining details. But when he put these Perival observables and found exactly the same answers that people got from matrix models, that's how he said that, no, my ideology is okay, I can do whatever people in matrix models can do. So this was his achievement. Okay? And if you have such a thing, O is called gravitational descendant.
Andrei, I'm not sure I understand the formula on the board with these two integrals on the left and right.
This formula.
Yeah.
So Okay. So here is a picture, okay? This picture means that you have a differential form on the moduli space where we have observables at marked points,
Okay.
okay?
Yes.
I can write a long expression that I wrote several times, but I'll repeat it again. So you have O at point Z1.
Mhm.
You have OI at point ZI. And you have Beltrami differentials multiplied by the superpartners of energy momentum tensor. And you integrate it. So here you integrate them over Riemann surface. And here you integrate over the modular space, because you interpret this correlator as a differential form. Once again, I remind you that you take a tangent vector, you take Beltrami differential, that's a map from the tangent vector to modular space to some field on the Riemann surface. You insert these fields, you integrate, you have the function on tangent vectors. So it is differential form. So if it is differential form, we can integrate. And that's what stands here. So you may call this a string map. It's a map from cohomology like this into differential forms on the modular space.
And where are these or sigmas or twiddles in this expression?
At the moment, not yet. I'm describing the left-hand side.
Mhm.
Now, just suppose that O equals to Z O tilde in cohomology.
Mhm.
Then I can replace insertion of O by insertion of O tilde times the first Chern class of the line bundle at point 1 understood as a differential form on the modular space. So
Mhm.
I hope that Z here and Z here will not be mixed up. So here I'll have integral over mgn of what? I will put here f at point Z1. Meaning, when I write f, I mean that I represent the first Chern class as a differential form. So this is a two form here. And then I have the rest. O tilde at Z1, etc. OI at ZI. Mu G, mu bar, G bar. This is also differential form. On MGN. Here I multiply two differential forms and integrate. Okay? And the statement is that this equals to this.
So this mu should be different in different.
The number of mu here and here should be different. Here the number of mu's should be 6g minus 6 plus n minus 2.
Yeah, I
You
was
see,
asking.
this do it because here we want to have this. Okay, I will not be lazy. 6g minus 6 plus n minus 2 form. And this is a 2 form. We can multiply and we have a top form. And we can integrate.
I was asking a more naive question. So for each of this mu g, mu bar, g bar factor, the pair mu bar is different at different insertions. So that those are kind of a differential form is fed at a k tuple of tangent vectors, of different tangent vectors.
Oh, of course. So okay. So let us repeat this, because people forget. So you need to understand this construction. It's very universal construction. So it's called string construction. It says that having that there is a map from h qz to the power n to differential forms on the moduli space. Let me repeat this construction. Okay? How this construction works. Take W1, W, K, that are tangent vectors to M, G, N. I would even write it better. I will write it omega 1 up to omega K1. Omega bar 1 up to omega K2 bar. So I take K1 holomorphic tangent vectors and K2 anti-holomorphic tangent vectors. So omega I belongs to T10. Okay, Pasha? I think I'm answering your question.
I can't see the formula, sorry.
You cannot see the formula.
No, because, sorry, you don't have to erase it. I couldn't see because you were standing in front of it. Sorry.
So omega I belongs to T10 MGN. Omega I bar belongs to T01 MGN. Tangent vectors, okay? So we take a tangent vector.
Yes, yes.
When we say that there is a differential form, okay?
Yeah, yes.
I will call it, let me call it ST correspondence or STR map. I take this tangent vector, I plug it here. So to say that I have differential form, I need to be able, given, so it means that given n elements here and K1 plus K2 elements of the tangent vector to get a number, right?
Hmm.
So it means that given O1, On, that belongs here, omega 1, omega K1, that belongs here, omega 1 bar, omega K2 bar, that belongs here. So this is an input. And from this input, I want to get an output. An output should be a complex number. Okay. Function on MGM. So what is differential form? I plug in tangent vectors, I get a function, right?
Yes.
So stir construction is this procedure. Here is an input, here is an output.
So this is what string field theory.
No,
Ah.
this is what universal string theory is, not string field theory, it's just universal string theory. And it's a pity that this string construction is absent in the textbooks on string theory. It's also a pity that this string construction is absent in books on Frobenius manifold and all that. The only place when you can read it in full detail are papers of Zwiebach
It's present in the
of
paper,
92.
it's present in the
Yes.
paper of Albert Schwartz and on topological field theory, the write-up of his
What is the year?
1990, 90.
Oh, Albert Schwartz always is ahead of time. So Zwiebach is 1992.
Yeah. So that,
Okay, Albert Schwartz, okay.
yes. So that
Okay,
is
I'm
close.
sorry. I missed the paper of Albert Schwartz in 1990.
It's a
Because
write-up
in
of his ICM talk. It's called topological field theory, I think.
You know? You see, in Russia, I wasn't at ITEP, and we got preprints at that moment. And whenever we got preprints from United States, we immediately copy it using Xerox machine. And we were studying them because we had the idea that the truth comes from United States, right? So somehow we ignored the people who were nearby, okay? And that's why I followed other people.
So that's a question in the WeChat, Andre.
Yes,
Mhm.
and Andrei, there was a question in the chat.
But still.
Mhm.
Okay, okay, thank you very much. I see. The question is, could integration go over configuration space only? At the moment, it is a differential form. See, I am not integrating it yet. It's a differential form. And of course, I can say that I'm interested only in configuration space. Moreover, when I'm writing this differential form, I'm not talking about compactification. This construction is about bulk. Yes, since it's a differential form, you can study only configuration space. It's also allowed. And I know why you are asking this. And by the way, I guess I know who asked this. So, because it's, so this question should be asked by collaborator of Chile. Yes. Who is doing this integrals of a configuration space, keeping the moduli MG fixed? Yes, it could be done. Here, it's not about integration. It's a construction of the differential form.
But okay, but we are not done here yet, actually. So we chose vectors, and we are supposed to. Mhm.
Whenever there is a question, Pasha, I should be very attentive to questions that come from the chat.
Right. So we are
So,
supposed
because people are shy to ask them.
right. We are supposed to
And I want to
feed.
encourage that.
Yes, we are supposed to feed all these vectors to Beltrami differentials.
Yes. So I will do it in an accurate way. There is a way to take this vector and to find a Beltrami differential associated to this vector. I want to say that this thing is non-canonical. It is a non-canonical map. So for one tangent vector, there are many Beltrami differentials that correspond to this vector. So I have to take some of them. So it's non-canonical choice. Different choices correspond to, so mu minus mu tilde is d bar of v. Okay. So how to write down the non-canonical choice?
Okay, so that's up to Diffie-Malfidon. Yeah.
It is better, you see. Yes, but when I say non-canonical choice, I need to say the following. So that there is a bundle, Beltrami differentials. So I know how to write it. Tangent vectors. And there is a projection. From here to here. So this is an infinite dimensional space. This is a finite dimensional space. So in order to do this, I need to pick up a section. Okay, S. There are too many sigmas. S because of section. So for omega, I need to take a section of omega that belongs to Beltrami differentials on sigma. Okay. So for tangent vector, I have a Beltrami differential. So now S of omega would be Beltrami differential. So how else can I explain this? Now, I take a section. It means that I pick up.
Do you fix a gauge or what do you...
No, I'm not fixing a gauge, any section.
Mhm.
So I may take any representative.
What is this formula with Neutrino? What's Neutrino?
And here are different sections. So different sections.
Mhm.
So I have many sections.
Ah,
So that they differ by d bar of v. So projection is such that d bar of v goes to 0. It's a description of projection. There are many Beltrami differentials. There are infinitely many Beltrami differentials, finitely many tangent vectors. Okay? So there was a projection. And by the way, there is no canonical section. At least I don't know what would be a canonical section.
Well.
So, still. So having this, let me make the map. I will consider the following correlator. O1 at point Z1. Okay, I call it P. Why should I call it Z? P is better notion for a point. On at point Pn. You see, when I write P, so P is not only for polynomial, P is for a point. Point is more important than polynomial. Then I have integral. Sorry, not mu. S of omega I, of omega 1. Okay, I'll write omega I. G. Take a product from 1 to K1. Then take a product for I going from 1 to K2. Here I take S of omega bar I G bar. So this is a correlator. Here are inputs and here are inputs. And this correlator depends on what? It is a function on the moduli space. So this is this differential form.
So then, well, the question which prompted this was whether you should write an index for mu. Should it be mu or mu I, and mu bar or mu bar I? When you
Okay,
write this
so the
formula.
question is what is F?
So here it says there's no
Okay.
mu, there's S of omegas.
Okay, so let me comment on what this means. You see?
But it sounds like there should be an index accompanying mu.
So people write it this way. So in physics literature, you can find it. You can find it in this way. So this is section of the cotangent bundle. Cotangent bundle of the type 1, 0 square. You see, when I write these, mathematicians feel very uncomfortable. But this G belongs here. It's a so-called quadratic differential.
Nothing
I don't
uncomfortable
like
there.
this terminology,
It is a 19th century.
but that's what it is. And this belongs T star 0, 1 times T 1, 0. And then I have a canonical contraction. So this product belongs to T star 1, 1. And this is 1, 1 differential form on sigma. of course. Okay, if you don't like T star 1, 1, I will write it T star 1, 0 times T star 0, 1. Okay. And this I interpret as differential form on sigma.
So if you choose G as holomorphic, so then different choices of sections of nu
Of course.
inverse
course.
same. Yes.
So it is a piece of the axiom. So here, this is a construction if d bar G equals to 0, and also is not too singular at marked points. So what does it mean be not too singular at marked points? It means that G should have no poles of second and higher orders. Because you see, if G is holomorphic, yes, this condition is too strong. What do I mean when I say that P's are marked points? I mean that it is possible that G could have a first order pole, and it's because consider as an example Beltrami differential or a section. The following section. Take mu that is zero outside the disk di around point pi. Take that's one thing. Then, what is mu inside this disk? Take V. Okay.
So Andrei, now you're describing a particular tangent vector to MGM.
Yes, I just want to show. Okay, I can describe how to get this construction for this particular tangent vector. Maybe it would be instructive.
Mm-hmm.
Because you see, I stated that there is this map.
Mm-hmm.
But then you may ask how it works. How does it work?
Mm-hmm.
Because when I say, I forgot one thing in the definition. I said that they should, that mu is equivalent to mu plus d bar v. But then the question is, what is v? I forgot to say.
Mm-hmm.
V should have zero, should be zero at marked points. You see, I'm writing this formula for so many times that I forgot that I need to stress it. That V in this equivalence should be zero at marked points.
Mm-hmm.
So suppose this is a Riemann surface, and let me pick up a very particular V. No, not V. I will pick up mu. That would be d bar of theta, and this theta is the step function on disk di times ui. So u times u. So what is u? So this is point I. U is a tangent vector at pi. Okay. So I can write this formula because I can write this formula because I can trivialize everything in the small disk outside this I.
So yeah, I understand the formula, but I didn't understand the picture. What's the picture?
So this is sigma.
The
I'm
line
trying
is-
to depict.
The line is sigma.
So that's how mu looks like.
Mm-hmm.
Mu is kind of a skyscraper
Okay. Okay. I understand the picture. Okay.
on the boundary of the disk.
Mm-hmm. Yes. Yes.
Or in other terms, mu is delta function on Si times u. So here is sigma. Here is the point pi. This is Si. And this is di.
I don't know if it's.
So when I take d bar, of the step function, I get contribution from the boundary. So this formula is the same. I just want to write it down in two ways.
I guess if you write down delta of SI, it should be some sort of a del bar version of delta.
Of course. So I'll call it 0, 1 version, yes. So actually what I mean is written here.
Yes.
I trivialize the tangent bundle over the disk. Or I can do it. I take a tangent vector at a marked point. Trivialize. I take a step function. It also exists. I take d bar.
Mhm.
I multiply. You may ask how it would depend on the different choices of trivialization. You will see that it will depend in a trivial way. But I actually have this. The formula downside is good in understanding what is going on. When you see this formula, it's clear that this is a 0, 1 form that takes value in the tangent space.
Mhm.
This is really mu. But when you write d bar of theta, you know that it's delta function on the boundary. So you may use either this formula or that formula for your convenience. Okay?
Mhm.
And I present both of them. Now, the integral of mu times g, this mu, inside something, here over sigma, it is the integral over s I of g. And here I have O at point pi and something else. And here I have not only this Si, but I also have U. And when I have this integral, I should look at the first order pole here.
Oh, but did we actually have an observable at pi? So
Yes, O at pi means that there is an observable at pi.
mm, okay. Mhm.
So I'm looking at this first order pole, and this is the contribution of this first order pole that stands here. And here is this U. And when I say that U is a tangent vector at pi, I just mean the following identification. That MGN is fibered over MG, okay? And then vertical tangent vectors. So there are vertical tangent vectors correspond to tangent vectors to sigma. So to change Riemann surface with marked point is to move the marked point. And this U is exactly the displacement of the marked point.
Yeah.
Okay? That's why what I'm doing here is this. I'm looking at the first order pole and I multiply it by U.
Mhm.
And this object is called first Witten's descent. This object. The result of the integral. So this first Witten's descent is a one form on the Riemann surface. And to see that it's a one form means that here it's constructed with u, with a tangent vector. So that's how it works. So would G have no first order pole? Well, the answer would be 0.
But so this is motion along very special moduli. No,
Yes, yes. This is motion along very special moduli, along vertical moduli.
I'm confused. So OP1, OPI is one form over the.
No, OPI is an observable. It's not a form yet.
Okay, it's observable.
it's a zero
So,
observable. Right?
so when I say it's an observable, it means that it is a function of local fields and conformal field theory, or just operator on conformal field theory.
So you mean
At the
zero
moment, it's not,
observable, right?
it's not a form code.
Okay.
When I'm using this construction, what do I do? So I
it's like-
identify tangent vectors to MGN, some special tangent vectors, to tangent vectors to Riemann surface, because they correspond to the motion of the points.
So OPI is probably a vertex operator, for example.
Yes, of course.
Yes.
They are, of course, vertex operators.
Okay. So now you contract with G. You have.
Yes, and I see the first order pole.
So you
You see, maybe I said too many things simultaneously, and that's why I confused. Pasha, it was your remarks that I'm trying to condense ideas and it prevents understanding. Right, Pasha?
That happens.
So I'll go slow.
Wow, that's why I had a.
So at the moment, okay, let me forget this remark for a moment because it's confusing. It's correct, but this is confusing. You know, you may say correct things that are confusing understanding, right? So you see here I made this computation. I took this mu like this. I made the computation and I found that I have u times the first order pole. So it is an example of the computation.
It's OP of G with O.
Yes, exactly.
Yes.
And here I see the following. Here I see that the first order pole contribute. And you may ask, what about higher order poles? And I will say, no, higher order poles are not allowed because in this case, would I have higher order poles? Everything would depend not only on the position of the marked point, but also on the local coordinate system at the marked point. And that's what I don't want.
That was this discussion of this decorated moduli space, right? Twiddle.
Yes, exactly. Yes, exactly. We discussed it already. So basically, this is a repetition, but
So you try to
since
put
this-
a descendant, like not a primary field, but some descendant, then things will break down in this way. Like Virasoro descendant.
we will come. Okay, so we will come. So let us discuss this in details because even if like 1 month ago, I explained it once, but the idea is not that I explain something. The idea is that you will get it. right?
It's fine. I think I understand what you meant.
So there is this construction. So this is an example that for the vertical tangent vector, we can take such mu's.
Well, if you have high order, you take a residue. So high order will not contribute.
If so, no, it would contribute, because if we have higher order, we need to take derivative somewhere here.
The invariance with respect to these will be broken, right?
So would we have higher order pole here? Yes, exactly. So that's what Pasha says. Suppose we have higher order poles.
Yes.
Then this invariance would be broken. Namely, we need to check that for vector field V that has zero, there is no contribution. So let us see that if G has a second order pole, we have a problem. Okay? So to see that we have a problem, let us consider the following example. Let us consider mu tilde, not mu tilde, mu two tildes, you see? That is d bar theta di times what? Times z times u, where z is a coordinate such that z equals to 0 is equation for pi. Okay?
Okay.
So you see, I picked up a very particular. What I did, I picked up a very particular mu two tilde, that is z times u times d bar of theta. So the statement that I would like to say is that this mu two tilde is d bar of what? Of theta di z times u. Now, this is a vector field, right? It's a vector field, okay? This vector field is not equal to vector field Z equals to 0 at pi, because Z equals to 0 at pi, okay? Of course, this vector field, by the way, is not holomorphic because of theta. So this thing, we would like this thing to decouple. When I say decouple, it means that putting mu tilde here should give us 0. Okay?
So, okay. So then if you take this integral,
But when so let us see what would happen if I put here mu two tildes. I want this thing to decouple. However, this integral is exactly the same as integral over SI of what? Of Z times U times G O I. And if G has a second order pole, I see that it doesn't decouple. It doesn't decouple. So if G has only first order pole, this field decouples. If G has a second order pole, it doesn't decouple. So that's why I'm allowing only fields that do not have second order poles with G.
Okay. I still cannot see how you can get a form on the modular space, on the Tashmiller space.
Okay, so let us see. So I discussed this arbitrariness. Still,
Yes.
I wrote this formula.
Mhm.
So I have
So this integral
I
is
have
in
10 vertex operators.
Yes.
I have K1 plus K2 vectors. I
Right.
compute this, and this is a function on the modular space.
I mean, this is as a correlation function from conformal field theory.
Yes,
Okay, so you need the conformal field theory
of course.
to do the integral.
Yes, of course I have. I assume that I have
Yes.
it from the very beginning.
Yes.
Of course, it's not. So it's of course this. So this is of course in conformal field theory.
Right.
So all were just local observables in conformal field theory.
Yes.
I'm writing this formula.
Okay.
So actually, what's important is that I can use this formula not only for cohomology. Actually, I can write it for all local observables that are not too singular in presence of G. So actually, the string construction is even more general. So I'm sorry. So I should put it not cohomology. I should put it like this: local observables times okay, I'll rewrite it in this way. So it is a map. So it's an input. I have local observables.
Yes.
I have K1 tangent vectors of the holomorphic type and K2 tangent vectors to anti-holomorphic type. And as a result, I want to have a function. So this procedure is correct. I would say consistent, how to say it, it's defined. Only if G does not have second order pole with local observable. So in this sense, I should say that I consider not all local observables. I don't know how to call them. These are called horizontal. I'll call them horizontal local.
Why horizontal?
So horizontal local observable O is horizontal local if G and O has no poles of order 2 and higher. Okay,
Why,
so then construction is like this.
why horizontal?
Why horizontal? Because in some sense, G is super partner of energy momentum tensor. So it is like contraction.
Hmm.
So let me put it this way. So if I eliminate what's horizontal local, I will get function on MGN hat, where MGN hat means the bundle over MGN with a jet of local coordinate.
Mhm.
So that I explained this already, but maybe it's good to repeat that there is a bundle MGN hat over MGN. So here you have a marked points. And here you have marked points with jet of local coordinate. So it's an infinite dimensional bundle.
So that was the Zweibach idea. Yes?
Yes, it's what's written in Zweibach.
Hmm.
So there is a map from all local observables. And then here you will have this tangent space to M like this. There is such construction. Okay, maybe I need to put all constructions on the board. There is this construction. Any local observable, any tangent vector here, okay? There is such a construction. Any local observable, any tangent vector to MGN. So what is a tangent vector to MGN? Okay. So first of all, what is MGN? So MGN with the hat is the moduli space with n marked points. With what? With jet of local coordinate at each of marked points. So now let us see. What is a tangent vector to MGN? Tangent space to MGN is what? Is a space of Beltrami differential such that mu is equivalent to mu plus d bar v such that what? Has, how to call it, infinity pole at marked point. Oh, it's infinity zero. Oh, previously we studied this identification where V should vanish at marked point. And now I would like V to vanish together with all its derivatives. Okay? So what does it mean? It means that when I make this identification, I am keeping the jet of local coordinate, because derivatives of V change the local coordinates. Because energy momentum tensor, what it's doing? Energy momentum tensor is changing, is a generator of diffeomorphism, right? So to see that such a map exists, okay, I still would like to call it string map. I don't know, Zwieback, Schwarz, I don't know, S. You consider the same formula. And now you see that when you change mu by d bar of V, you can take an integral, and any pole between G and O would not contribute, because V is vanishing very fast. The poles with G just do not contribute. So this is this map. And then we would like to have a map not on this moduli space with the hat. We would like to have a map on the moduli space itself. Okay? That's why we have to restrict. What we call the local observable. So how are we restricting the local observable? First of all, we would like the local observable to be independent on what? So here there was no restrictions. Now I want to put more restrictions. Now I come into restrictions. I want to go from MGN head. I want to go to MGN. So I need to consider the invariance and horizontality. So it's a well-known thing. If I have a differential form on the total space, and I want to have differential form on the base, I need to impose this condition. Invariance and horizontality, right? So what is the condition of invariance? Condition of invariance is invariance. Means that energy momentum tensor with O does not have pole of order 2 or higher. Okay, so this means invariance. Pole of order 1 is allowed because I consider this point as marked. Pasha, is it clear?
No.
No.
Oh, let me think.
So this makes a diffeomorphism. If V has 0, so I want this to be 0 for V of 0 has a simple zero.
Mhm.
So first order pole is allowed. Second order pole is not allowed.
Mhm. Okay.
Third order pole is not allowed. Because what does V that has a simple zero? So V that has no zero shifts the point by its value.
Mhm.
V that has a simple zero, but is like Z. Okay, it has simple zero. Makes a dilatation of local coordinate.
Right.
So if I write V of Z as Z to the L d over dz, I
Mhm.
see that L equals to zero corresponds to fifths of a point.
Yes.
And of course, we should not consider vanishing. It's a dependence that we are going to study. L corresponding to 1 is a dilatation. Z d over dz. Rescaling.
Mhm.
L equals to 2 is something given higher.
Mhm.
So if we start L equals to 1, 2, etc., these vector fields, what they are doing? They are changing the jet of local coordinate.
Yes.
These change the jet. So if we have local coordinate Z, that L equals to 1 is like this. L equals to 2 is Z plus lambda Z squared. Okay? So these are changes of local coordinate. So when I say jet of local coordinates, of course, I mean coordinates such that they are zero at marked point.
Mhm.
Maybe I need to phrase it. So we have these restrictions.
Mhm.
But this is only invariance. Okay?
Mhm.
Now we have extra restrictions. And this means horizontality. And you should ask me why. I call this horizontality. So this is horizontality because non-horizontal means that you contract with a vertical vector and you have something non-zero.
Mhm.
But these vector v, so smooth v that have what? That have zero of higher orders correspond to what? To vertical vectors. So horizontal things are such, horizontal forms are such that when you plug in vertical vector, you get zero, right?
Mhm. Yes.
So that's why horizontality means that always such that if I have here vertical vector and vertical vector here when I have S1, in S1 picture, vertical vector is what? Z to the L d over dz. L greater or equal to 1. So these are vertical vectors. I have here a differential form. I want this form to be horizontal. So how to check that it is horizontal? I put here vertical vectors, okay? And my condition is that the result should be 0.
Mhm.
So horizontality of the output differential form means that G should not have higher poles. It is the condition of horizontality of local observables.
So there was at some point a string condition G naught minus of something vanishing. So that's a weaker version of this.
I'll come to it. But at the moment, you see,
Mhm.
for me to explain this, I need to start. You see, I need to explain it in steps.
Mhm.
So before all this,
But it looks like
I
a
have this.
weakened version of this horizontality.
Yes, yes. So at the moment I have this.
Mhm.
Okay. So let us see what kind of constructions do we have. We have this construction on the top. No conditions on O, just conditions on being local. Okay. And for local fields, we have this map. We have differential form on M hat space. Now, consider horizontal. Okay, maybe invariant on horizontal. Let me call it invariant horizontal local observables.
I think invariant and horizontal objects are usually called basic.
Ah, right. Good. Basic local observable. I will not be lazy. I'll write all formulas, you see. MGN. So what is important is that here I have no heads at all. Here there are heads, and here there is no heads, okay? So from basic I have this. From local I have this. So there are two constructions. This one, so this gives this construction and this construction. Now, I can play with it. Now I can look the following. Now I can look at the following. The manifold, the bundle MGN hat over MGN is contractible to Marita-Mumford bundle. Okay? So it's true. Sorry, I wrote it in an ugly way. I need to write it like this. MGN, let me call it Marita-Mumford. So with fibers, you 1 to the power n. So when I'm doing this construction, or I'm thinking about this construction, I'm thinking not about forms. I'm thinking about cohomology. Okay. Because before I do this, I was talking about differential forms.
So
But
UI
now,
is the rotation at each marked point.
yes, U1 is the rotation at each marked point.
Yes.
And first of all, I may say that, okay, when I say that it's contractible, it means that I can, in principle, pick up local coordinates in such a way that there will be only one rotations among them. That's when I go from chart to chart. You see, it's that means that it's contractible. No obstruction. Moreover, I can have different equations in mind.
So contractibility question seems to indicate that you're passing from looking at forms on M hat to looking at closed forms on M hat.
Yes, that's what they said. If I'm interested
right.
in cohomology.
Right.
Yeah. I said it, but I have not put it on the board.
Mm-hmm.
So I'm interested in contractibility if I'm not looking just in this game, if I'm going to integrate differential forms.
Mm-hmm.
So if I'm not going to integrate differential forms, if I'm going to study correlators for some purpose, I have just this and that, okay? But now I would like to study these differential forms that are defined here in cohomology, okay? So if I would like to study cohomology of them, of all of the constructed differential forms, I can study the issue of contractibility and I can do many things. So it is so when I'd like to study such differential forms, I'd like to do what? I'd like to see what happens if, okay, I will put it this way. So now I'd like to construct closed differential forms on the moduli space, okay?
Mm-hmm.
So now I'd like to, or to study cohomology of the moduli space. So first idea is that I should impose condition that Q on log equals to 0. Second, I can say that I can go from log to log times descendants. It's still called Z, okay. So what would this mean? This would mean that I'm multiplying so this is differential form. So okay, so since I explained differential forms, yes,
Mm-hmm.
I can say that then I have the following map. I'm thinking. I think I would like to put here cohomology of Q to the power n into
There's a cutoff on the blackboard.
So now the cutoff is here.
Mhm.
Into cohomology of MGN. So I multiply cohomology of Q by polynomials in Z, in formal variable. I take the nth power. I want to define this map. So after I define the string map, let me call it Koch map, okay? So Koch applied to what? To Z to the power K, L1, O1, Z to the power Ln, On is mapped to what? Is mapped to F to the power L1, wedge F1, Fn to the power Ln, and here I have string of O1, On, okay? Where Fi is what? Is a representative, is a two-form representative. Of first Chern class at Li.
So you probably have different Z's.
Yeah,
So
exactly.
Fi, yes.
Mhm.
But you see here, not different Z's. Here the argument is C of ZHQ.
But you only have Z or Z1, Z2, Zn.
No, this, okay. So they correspond to different, to different places.
Which is the same as to put an index on them.
Because you see, when I say this,
Ah.
I am not saying that this is Z linear.
Oh, okay. I see. Different mark point.
But you cannot take Z out of it. That's the point.
Yes, I cannot. I'm not taking Z out of it.
Yeah.
Yeah.
I'm just writing. So elements here have a basis ZL1, O1.
Mhm.
I'm not going to take a Z out. So this map is C linear. Okay.
Mhm.
So when you say you cannot take Z out, of course, yes. I also cannot take this one out of it.
No,
I cannot say that it's 1 times O. No, 1 belongs here.
right. No, but this is tantamount to saying that you can decorate Z with index corresponding to the puncture. But, I mean,
Yes.
you don't want to do it, but it's
So
just an
here,
interpretation
so
of it.
this is exactly to say that I have 1 L1.
Okay.
Okay.
Yes, so here I gave a definition. What do? I already described this string construction.
Mhm.
So this is a differential form. And here I multiply. This is again a differential form. Being a product of two differential forms, it's a differential form, it's a closed differential form. Now, how do I know that this form is closed. I have not checked it.
So,
Yes?
no,
Yes?
Andrei, just to, it would make sense to decorate Z with an index because it's an equivalent parameter corresponding to a line bundle, and the line bundles are different for different punctures. So just saying.
Let me see. Okay. Okay. So, but this is notation operation.
It's a
If this is
notation,
not
yes.
transparent,
Yeah.
because you see, when I say CZ, you see that, as you say, that if it's not Z linear, it is not good to.
It's
Okay,
a little bit
I see.
confusing, but
To call it the same Z. Okay.
Mhm.
So it is like this. Now, what I need to show? I need to show that if that here, so this is this defined if Q of O equals to 0. Okay. So now we need to move. We should have breaks sometime. So once again, I'll have a robot who will tell me that we need to have a break.
well, as you say,
Okay, so let us make the 5 minutes break. 5 minutes, but we need to have breaks.
all right, okay.
Otherwise, it's not fair. You see,
Yes.
I always promise that we will have breaks.
Okay.
So we can do everything, but only if we will have breaks. Okay?
All right.
Я тебе всю работу прорву. Где мои киндер-сюрпризы, а?
So. Okay. So now we can continue. So I want to show the following, that if O's are closed with respect to Q, then this differential form ST is closed. The proof is the following. Let us apply D here on the moduli space. So when we are applying D on the moduli space, what are we doing? I'm thinking the way in which I am thinking about the best way to explain this. So the easiest way to explain this is to explain that we take derivatives along moduli space, and these are done by insertion of energy momentum tensor. Okay, let me give you an idea that when you take derivative, you do the following things. You have O1 at P1, On at Pn, and you have T times. I know how to explain it. Sorry. So first I need to understand what is the derivative of this differential form of the moduli space is. Okay? The derivative of this form is a K1 plus K2 plus 1 form, right? And we need to study this form on the set of vectors, omega I, omega bar I, and also one more vector. Let us call this, so this would be omega, let us call it omega 0. We have an extra vector. So I am mimicking the following formula. That for ordinary differential forms, d omega on the set of vectors, omega naught, omega 1, omega k is what? It is, as we know, L omega naught of what? Of omega applied to omega 1, omega k plus what? Plus omega, and here we have something like omega 1 bracket omega naught, omega I, omega k. So I'll try to imply this formula for vector fields, not for vectors, but for vector fields. So what would it mean to study this term, L omega naught? It would mean that I have this, okay, product of O's, OI, and here I have L omega naught means that I have this S omega naught, and here I put energy of atom tensor, and the rest, this SG, S G bar. Okay? So this insertion of energy of atom tensor is like this, L omega naught. But then there are other terms where we have omega naught, omega I commutator. Product from I equals 1 to N, OI, and here I'd like to have these commutator terms, SG, SG bar. However, here I'll need to put here omega I, omega naught. Now let us see why this could be. Why it's very probable that this identity holds. Why this could be zero? It is because energy of atom tensor, that's it here, is Q of G. Then I take this Q out. It could hit either O's, but now I assume that O's are closed. It also can hit terms here. And in this way, I hopefully get the second P. So here I am not giving a proof. Here I'm giving a sketch why this thing is closed. In order to make a proof, I need to explain it in more detail. Why it is like this? Why exactness of energy momentum tensor actually means the differential form is closed.
So in the formula for the RAM differential, you need omegas to be not just vectors, you need them to be vector fields to make sense of Lie bracket.
Yes, yes. And there is an arbitrariness here. Because when you like to study the closeness, so it's a way how I know how you can try to do it.
So previously for us, omegas were just tangent vectors. We fixed the background.
Yes, yes, yes. So that's why what I wrote here is not a proof but a sketch.
Okay. Mm-hmm.
Because you see, I have a formula. I just need to know how to. So what is external derivative of differential form? So what kind of differential? So what kind of definition should I use? The only nice definition that I keep in mind here is this one. So if you have some other formulas, so suppose you have a differential form, okay? How would you define the DRAM operation acting to it without picking up any coordinates? So what is DRAM? So actually, it's kind of the only definition that
Yeah.
that I have.
You know, one could say that this second ugly term with the brackets is needed because the first term is not what's the word? Is not a infinity of M module. So I mean it.
Yeah.
Yeah.
Yes, because we need to take the derivative here.
Yeah. So it's a compensation term.
Yes. So when we take derivative, it means that we need to transport the tangent vector omega 1 somewhere.
Mhm. Yeah.
So there is an arbitrariness in this transportation. That's why we have these terms. So, but you see, once again, this is the sketch
Mhm.
of the argument. And if you ask if I have the better argument, it always goes like this. You see?
Mhm.
I don't know definition of external derivative without differentiation. And differentiation means you need to make a transport.
Yes.
Okay. So how can you make a transport? So the only way to make a transport is, of course, to transport everything here.
Right.
So it's my excuse why I cannot show you the nice looking proof. Okay.
Well, and any other ways to combine with homology. So it's kind. So
How can
So
you want to say that that's another way to prove is to show that the integral with over any boundary is zero.
yes,
Huh?
yes, yes.
So okay, Sen has an interesting idea,
Mhm.
but how can I do it in a constructive way? I still need. So in order to integrate over the boundary, I still need this form to be defined not at a point, but in the region where I have this boundary. So it is somehow equivalent.
Yeah.
I will still need to have this transport.
Yeah.
So, but it's okay. But we are not writing the nicest textbook about it. Okay, we are trying to understand what's going on. So it is so technically, it is a bit complicated to prove it, but it's just technicality.
Mhm.
So idea is so the easiest way to prove it is when K1 and K2 are 0, then there is no problem. So for function it's clear. However, for differential forms, you see, you need to make a parallel transport. Parallel transport is done by energy momentum tensor. So you need to transport on the bigger space, like MGN hat. And then you need to put things down. So unfortunately, it's a standard problem. It's a standard issue. It's not very easy to define the external derivative of differential form without transport, because you differentiate. Okay, so since you are teaching calculus, you understand. Okay, so it is closed. That's why that's why I have this. Koch. Okay, it's easy to hide under Z N L N O N. F1 to the power L1, Fn to the power Ln, and here we have string O1, On. So this is closed, these are closed, okay? So it's a good product. So it's a product of to total derivative. So it's only cohomology class of this F1 that is interesting. Similar here. So that's why Koch means the class of this in the round differential over the moduli space. It's a class. So among these classes, we can take the top class and integrate. But we do not need, so we can leave it like this. Now, let me explain that if we put that
So,
cohomology of QZ, so how cohomology of QZ is related to this space.
So, Andrei, what did you say about why about the ambiguity? Why this is not well defined before passing to the cohomology, to the RAM
So
cohomology?
it is defined, but there is no use of it. Because when we have here the first Chern class written as a differential form.
Yeah.
So the question is how you are going to use it. Maybe I was too radical. If you know a preferred connection,
Yeah.
you can write it in terms of forms. And you see, after I said that it has no reason to have this formula, I immediately felt sorrow. And I felt sorrow because of the following reason. If we study tropicalization, there are preferred connections. And that's why this formula is also interesting. But you see, now let us discuss relation of cohomology of QZ with this.
So how did Z enter? So it was.
So QZ was Q plus Z, G not minus. So here we see a covariant differential. So let us recall the following, that if O is Z O tilde in HQZ, then Koch of O and everything else equals to Koch of Z1 O tilde up to total derivative on the moduli space. So namely that this z that stands in this differential and this z that, as you said, is like bookkeeping parameter, yes, are the same z's.
Mhm.
Okay. So how can we do it? Consider this condition. So what does this mean? When such thing could happen? Such thing could happen. So what do we see? We see that this should be q plus z g naught minus of something that, let me call it A capital. Okay. So O minus 0 tilde. So what does this mean? So let us see what this means. It means that O is Q of A capital. And O tilde is G naught minus, so up to the sign of A capital. Okay? So it means that O looks like being exact. But it is a mock exactness because it's exact of something that is not horizontal. Okay? So when I have correlator of O, I have a differential form on the total space. And when I want to bring it down to the base, I have to do something. And that's how I am getting this F. So it is a scenario. Let me show how it works. Okay? So consider the correlator of O. Okay? Then I replace it by Q of A. And this is already differential form on what? On the total, on Yuan bundle over MGN. And not a differential form on the base. Okay? Sorry, no, sorry. This is differential form, I'm sorry. This is differential form on GN. But if I'd like to pick this Q out, it will be differential form on the total space. So what can I do? I can do the following. Sorry, I'll write it down in a second. I would like to consider A improved. Namely, I'd like to consider A minus A capital. So what is A capital? So this is one form on the MGN such that dA is F1. So what does this mean? It means that I can lift A. So what do I mean here? So it is not actually one form LMJ, it's one form. I'm sorry. So A is a one form, I'm sorry, on the total space. So it's a connection in the line bundle. Now what I'm going to do? I'm going to do the following. So I have this guy. I want to explain why I can replace this Q of A. Let me put a question mark. By what? By O tilde times F. That's what I'm going to do. So I want to take the difference. So Q of A minus F. And here I have O tilde. So on the total space, this object is exact. And this object is also exact. On the total space, on L. Okay? This object is exact because here I have Q of A. So it's exact observable. This object is exact because it's D of A. And this is closed. So this is exact on the total space. This term and this term is also exact on the total space. However, this is not horizontal and this is not horizontal. Okay? And this is not horizontal. So what I'm saying, sorry. So excuse me, so once again. So this is an exact and this is exact on the total space. However, A is not horizontal. And A capital O tilde is not horizontal. So this thing is exact. However, the preimage under Q is not horizontal. And this thing is also exact on the total space. However, the preimage is not horizontal. Preimage of differential. Okay? So what is good about taking this difference is that this thing is what? Is D on the moduli space of what? Of A and something minus A O tilde and something. And now this guy, this difference is horizontal. Ah, now I got it. So now let us check that this is horizontal. So let us apply the U1 action. Here, application of U1 action here would give G naught minus A. Okay? And this is O tilde. Okay? Check of horizontality here gives we act with by U1, we apply it to A. And this is 1. And look, since there is a minus sign, this difference is horizontal. So this difference of this and this is D of something that is horizontal. So this is the argument. Why we can replace this by this? And that's, of course, there was a reason why I called this pre-image with this curly A, because it is like connection. So, okay, so is it clear how I reason? Again, I consider difference between two closed forms. So this is a closed form.
Andrei, what are you proving actually?
Sorry?
What were we trying to prove?
I'm trying to prove that if O is equivalent to Z O tilde in QZ cohomology,
Yes.
then in the main map, I can replace O by Z O tilde.
Okay. Yes.
So I'm trying to prove that O with anything else equals to, I would say, Koch construction of O and something else equals to Koch construction of Z O tilde with the famous. So that's what I'm going to prove. Where O and O tilde are related, where O and O tilde are related as follows. So the difference is Q of Z exact. And I keep A that knows how they are exact. So I do it in 2 steps. In first step, I see the following. That it means that O is Q of A and O tilde is G naught minus of A as local observables. Then I consider this difference in Koch. And I want to show that this is 0 in Koch. The question, is it 0 in Koch? So why do I think that this is 0 in Koch? Why I could even think that it could be 0? The left-hand side, the first term, is almost 0 because it's Q-exact. But so it is Q-exact, but of something that is not horizontal. The second term is D, DRAM, exact. But again, of something that is not horizontal. However, the difference is D of something that is horizontal. So how do I see it? I will construct this thing explicitly. The claim is that this difference is D of what? Of this curly A and something, and here A times O tilde. When I apply D, here I get Q of A. When I apply D here, I get F. Now let me check that this difference is horizontal. The first term is not horizontal. We have correlator of O tilde. The second term is also not horizontal because of this, but we still have correlator of O tilde. But differences of correlators of O tilde is 0. That's why the difference is horizontal. So this is the most tricky reasoning, okay, here.
So the Landau-Ginzburg model is kind of bookkeeping.
So Landau-Ginzburg model is an example where I discovered this phenomenon.
Hmm.
So I discovered this in '93. So actually, I discovered it in a different form, but late Eguchi, you know, he recently died, pointed out that the form should be like this.
Mhm.
So whenever I'm writing this formula using this argument, I always refer to Eguchi.
Mhm.
But after all these references, I just want to say that here is this consideration explaining that that was a parameter in the pencil is actually the gravitational descendant. So this Z was put in this form by Kyoji Saito. However, he never had an idea why it is gravitational descendant. So after this, let me consider an example. Example, W is x to the power n. Okay, if W is x to the power n, then let us see what is the differential. Q1 was d bar plus dw, and Q2 was d plus d bar w bar. 1, 2. Now, cohomology of Q1 plus Z Q2 are what? D bar plus dw1 plus zd plus z d bar w2 bar. So let us consider the case where w2 bar equals to 0. Then one can convince himself that cohomology are like this. dx, etc., dx to the power n minus 2. Okay, let me put here n downstairs, such that dw would be like x to the n minus 1. Oh, sorry. X to the n minus 2 dx. So x to the n minus 1 dx is exact. So it's exact in all senses, because x to the power n minus 1 dx is, of course, d. Okay. So when I say that this is exact, I mean that it is what? It is dw applied to 1 plus d applied to 1, this is 0. You can even put here z. So this is exact. What is interesting is what happens with xn dx. xn dx is x times dw. That is dw plus zd applied to x minus zd applied to x. So this is q of z exact, while here we have just up to sign minus z dx. So this is gravitational descendant, z dx. And actually, x to the power n plus k dx equals to what? dw times x to the power k. That equals to dw plus that d applied to the x to the k minus z d applied to the x to the power k. So it's minus z x to the power k minus 1. Okay, with a multiplier k minus, with a multiplier k dx, etc. So here we see that we have classes that are proportional to z square, etc. And the set of Q of the cohomology is like in the it's called nth reduction of KP. And this thing was actually discovered. This cohomology was discovered by Kyoji Saito this way.
Could you rewind 2 phrases?
Okay. So we go all this way down, and we see the following, that z. So we have these objects for k less than n minus 1. Z n minus 1 dx is exact.
X n minus 1 dx, right?
Yes, I'm sorry. X to the n dx is equivalent to z dx. X to the n plus 1 dx is equivalent to z x dx with some number coefficient. I'll call it number coefficient. It's some number, I don't remember. It's clear, so it's 2x dx, etc. Okay, not so okay, like 1, etc. So then we go to what? Then we go to x 2n minus 1 dx. So it is equivalent to z x to the n minus 1 dx. And this is exact. Then we have x to the power 2n minus 2n. That is equivalent to z squared dx, etc. So powers of x go as follows. They bring higher and higher powers of gravitational descendants. And this is what exactly was found in the computations that people have done. And what I'm showing you is an explanation how it works.
But you said some words about relations to KP. What could you say again the words?
Okay, of course. So how this is related to KP? There is it's called dispersionless KP hierarchy. No, you put it. So how to? Okay. Once again, you see, I forgot the spelling of English words. So dispersionless KP hierarchy. There you have so-called Hamiltonians. So Hamiltonians are made out of the L operator to the power k over n plus. And you have something like the prime here. Or maybe not prime when you write down Hamiltonian. And you have gaps. So when you study these Hamiltonians, sometimes you have trivial, so the set of times.
What is this L?
So it is L operator of hierarchy. So it is pseudo-differential operator such that its power is differential operator.
Mm-hmm.
And there are times in this hierarchy. And times in this hierarchy corresponded to integrable system that was known to describe topological gravity plus minimal model. So simplest case is the case where n was equal to 2. So when n was equal to 2, you have actually 1 z square or dx. Z dx, z square dx, that's it. So you have only gravitational descendants of the single element of the Q cohomology. And this was called pure gravity. And these were times of the KdV. It's times of the KdV. Okay, I think I need to explain it in some detail, not now.
Is it the Dubrovin's stuff?
So it was called Witten's conjecture. So it is Witten's conjecture in genus 0.
Mm-hmm.
And people were kind of confused. So people studied Landau-Ginzburg. People studied Landau-Ginzburg with the fields like this, and nobody understood how it happens. There are universal formulas. They see only these terms, and there are higher times. And people knew from the experiments that higher times, not numerical, from computations, they knew that higher times corresponded to higher Hamiltonians. So I studied this problem and I found all this. So I knew what I had to find. I had to find that higher axis that corresponded to higher times should correspond to gravitational descendants. So there is a question here. So the question is, of course, about Toda lattice. So the formulas, of course, are universal. So actually, the Toda lattice is not x to the minus 1. It's actually a sum of x plus x to the minus 1. You need to take 2 points out. So I have not studied the Toda lattice, but it's exactly what is needed if you'd like to study the mirror of the CP1 theory. Okay, now I think I'm out of time, okay? But I hope that I explained something.
Right.
Okay. So, so we are moving slowly, but we are moving, right?
Mm-hmm. No, sorry for.
Pasha, do you have a feeling that
No, I apologize for slowing you down dramatically.
No, you see, I need to move at the proper power, you see, at the proper speed. Because these are constructions that are not well understood. I mean, by the common audience. So some people used to them, but the reason of these studies, the studies of what we are doing, is to pass the information to other people. So what is a string construction? What is homological string construction? Why we are imposing this condition, that condition? Okay?
I might have been wrong about the time of the Schwarz's paper. It was some kind of round year. It could have been not 1990. It could have been 2000. I don't remember, but it was some sort of a survey paper.
Okay, so if it's a survey, it could not be 1990. But so
Yeah.
there is Zwiebach. So when Zwiebach wrote his paper, people were not very interested reading it, unfortunately. However, his set of papers had good ideas. So he got permanent position after writing these papers. That's good for him. But it will be good for the community if people study his paper with more attention. Because people at that moment went into doing matrix models, because it was easy to discover things in matrix models. However, when you are discovering things in matrix models, you need to understand that this is only a limited example. So geometry is bigger than just matrix models. However, I remember these days, everybody was doing matrix models. So people somehow forgot the general story. And it's a pity. So it was also the reason why nobody studied Zwiebach. Because I remember these days. At these days, people were telling, look, matrix model is a non-perturbative formulation of string theory. My goodness, why? Okay, it was a slogan. String theory is inside a simple matrix integral. So they were not being able to explain it in detail. Nobody cared. So matrix models of these days were discovering only small class of theories that were basically, okay, small class of theories, I would say, with a limited geometrical interpretation. However, people jumped on it and forgot geometry for some time. So these were 90s. And then the mainstream, so nobody studied Zwiebach. And then the mainstream jumped exactly to Seiberg-Witten stuff. So people decided that this is interesting. And again, nobody studied Zwiebach. And then after Seiberg-Witten, a so-called second string revolution came. And so everybody jumped into the second string revolution. So people had no time to study Zwiebach. So nobody was studying and thinking. People were trying to get hot new results. So would people dare to read and think about what a person is doing just to pay some attention? They would get all this.
Andrei, I think
Yes.
I should go.
Yes. So I think it's enough for today. And now, Dong, what are we going to discuss tomorrow? What would you prefer to discuss?
Okay. I think it is good to continue the discussion last week. But I have to say I'm very excited to see these hierarchies in this board, because this is exactly what I want to understand for the last several years, and they had no idea. So if you don't mind, you can explain it a little bit more tomorrow. It would be a very
okay. So tomorrow, I see. So we play this game. I'll explain I'll explain hierarchies, and I'll say that there are open problems. We related these hierarchies and Toda. Okay?
I would be
Okay,
very
so
interested in
let me
this
be
too,
a little
but
bit
I
more
cannot
explicit.
attend. So yeah, maybe.
Sorry,
I'll-
Pasha?
Sorry.
You said something.
I'm very interested in that story too, but I cannot attend sadly. So yeah.
Yes, so you see, so it means that, Pasha, please don't be unhappy. If it will be needed, I'll repeat. You see,
No, hopefully maybe if there will be a recording or something.
there would be a recording, but
Okay.
you would understand better if you'll have a ability to ask questions.
Right.
So,
right.
so tomorrow, I hope, I talk about hierarchies. Okay? What I know. So I cannot say that I know a lot, but what I definitely know is hierarchies at GNU 0, of course, and issues related to Toda. And I have some open questions there. So we can discuss this too. Since Friday is a discussion day, right? Then I'll put there not only statements that are clear, but also conjectures. Okay?
So let me be a little bit explicit. I know there is a result on this ADE singularities. Maybe that's the minimal model physicists usually call, that there is a corresponding Lie algebra and there is also a corresponding hierarchies. And this Jacobian ring of W with this Maritime-Mumford parameter Z somehow in a mysterious way recover all those hierarchies. I know there are some results. And I saw that there is a similar result for the mirror of P1. That's good. And I really wanted to know is there a more general stories for arbitrary singularities?
Okay, so I'll try. So this evening I'll try to remember what I know about this. Yes, and I'll tell you something, okay?
Okay,
And
that's it.
as always, my desire is to make it interesting and I want to satisfy your curiosity.
Just
Okay?
if I
And
can ask
tomorrow
you
we'll
can I ask you to record everything? Because I think those recordings that never end up in the this YouTube list where the kind of lecture recordings are collected.
No, there are recorded.
I don't think so. I don't think that those conversations that you
Really?
have that they end up there. I'm not sure.
Okay,
Are they?
okay. So I had all copies for this complimentary seminar. So
So if you have all copies, please send it to Pavel Mnov.
Not to me, to my father, to Nikolai Mnov, because
Yeah, of course.
I see.
he is uploading them to the YouTube.
Okay, so I have something in the chat.
Mhm.
So so the chat is asking construction of the pair WQ, of course. So concerning the pair WQ, yes, of course, there is relation, and this relation is so-called dilaton equation of Krichy-Ware. It's called WDQ equation. Okay, so am I right that the name of the person is Sin Singh? Okay. So who is writing? I don't know how to pronounce your name. So Sen, since you are Chinese, how should I pronounce the name of the